the Soliton resolution conjecture for the Benjamin-Ono equation. Thank you very much for your invitation. It's a great pleasure to talk here in honor of Sergio. You know, several speakers today made reference to 1986 when this technology of vector fields spread out, the whole of analysis of nonlinear wave equations thanks to Sergio. And that was almost exactly the time when we met. So it was 40 years ago. I was just an assistant professor at École Normale, and you were visiting Claude Bardos in the Centre de Mathématiques Appliquées at École Normale, and we met at that time, if I well remember. Since then, of course, I had the privilege to have a complete picture of, so far, of your contribution to general relativity, and which is so impressive. And despite Sergio's efforts, I'm still not working on general relativity, I'm sorry. But I made some progress because I'm interested in long-time dynamics of nonlinear wave equations, on nonlinear dispersive equations. And this is, in fact, what I'm going to talk about today. So this talk is based on a Franco-American collaboration after 250 years after Lafayette and Washington, maybe a slightly different purpose. So this is joint work with Louise Gassot from Rennes for the French part, and Peter Miller from Michigan. And I'm going to talk about some ideal nonlinear dispersive equation describing, if you well remember, the situation that Alex Ionescu yesterday talked about, which is water waves, 2D water waves, except that I will assume some strong approximation, which is the long wave approximation. And moreover, I will assume infinite depth. And this leads to an equation which was introduced in 1967, which is the Benjamin-Ono equation. So this equation, of course, as yesterday in Alex talks, describes the deformation of the interface between two fluids, let's say air and water, let's say, and with some gravity, no superficial tension, no surface tension. And so this deformation with respect to the equilibrium at time t and at point x will be denoted by u of tx, so it's a real valued function. And I will assume it's going to 0 at infinity. And the equation is the following: dtu plus dxu square minus dx mod du equals 0. So mod d here is the standard Fourier multiplier, and that's also the Dirichlet to Neumann operator for the upper half plane, which is in fact why we see it here. So what can we say about this equation? Of course, it's a nice Hamiltonian equation, and it's very natural to study the well-posedness of the initial value problem, the Cauchy problem, let's say. So this problem of global well-posedness I'm not going to talk about because it's completely solved. And it motivated a lot of attention on a very long time. In fact, let me see this. This is the time of mathematicians. And this is, in fact, the S in which we were able to solve this equation. So it started in 1979, and, well, it continued to 1989 with Jean-Claude Saut and his collaborators, including Benjamin-Ono. And that was for H2 to H3 half plus epsilon. Then came a contribution by Gustavo Ponce in 1991, which corresponds to H3 half, which is not so clear because you know you have something quasi-linear here. So you need some Lipschitz estimate, and you don't have it a priori. Then came a very important breakthrough in 2004. So we gained 1/2 derivative, and it was based on a very nice, well, I will not say gauge transformation, let's say normal coordinates or whatever, I don't know, introduced by Terry Tao. Then we went to L2 in 2007, and there were a very nice result by Alex Ionescu and Carlos Koenig. And well, it was revisited 5 years later by Molinet and Pilot, who simplified their proof. And finally, in 2019, by Ephraim and Tataru, with a completely different proof, and with some estimates, dispersion estimates, on very long time, exponentially long time with respect to the small size of data. So this is for L2, but this is not the end of the story. The end of the story corresponds...
The last one is still L2.
Still L2. Everything is L2. And now the end of the story corresponds to the criticality of this. This is H minus a half critical. And in fact, you can solve the problem in the sense of extending the flow map continuously to H minus a half plus epsilon, and that was proved in 2024 by Kilip, Lawrence, and Monica Vision. So this is a nice list of contributions. But now we can say that for any initial datum S, for S bigger than minus a half, I can define my solution. And moreover, and this is related also to some very important property of this equation, moreover, we have bounds in HS on the solution.
This is also the scaling exponent?
Yes. And the case, the critical case, H minus a half is violated. We know it's ill-posed. Okay, it's ill-posed. Okay, so this is the real. So why is that true? We will see, because it's related to a very important property of this equation, which is some kind of integrability. And here it's related to conservation laws, many conservation laws, which essentially control all the HS norms. So it's quite an ideal situation where you have control of all the HS norms for S big enough. Now, the question is, we want to go further. Well, a little bit like in Sonjing's talk, we would like to describe the solution as t goes to infinity. Long-term asymptotics. Can you describe u of t as t goes to infinity? To have this in mind, if you have this in mind, you need to know a little bit more about special solutions of this equation. There are special solutions which are traveling wave solutions. And in fact, these traveling wave solutions were already observed by Benjamin in his 1967 paper. So traveling wave solutions are of the form u0 of x minus ct, and Benjamin observed that special profile u0 were of that kind, Rp of x, where p is a complex number of positive imaginary part, and Rp of x is this guy, twice the imaginary of p divided by modulus of x plus p squared. So if you prefer, it's a Poisson kernel. It's a rational function which is up to a constant, the Poisson kernel, in the upper half plane. Okay. So in that case, the velocity is positive, and it's given by that will 1 over imaginary part of p. Okay. So what does that mean? It means that you have this function here. If you start from at t equals 0, and as t evolves, it will translate to the right, only to the right. C is positive always. And it translates without changing, so it's what usually people call a soliton. So these are special solutions. And of course, if we want a rather general long-term asymptotics result, we should keep in mind that this soliton at some point should play a role. Well, in fact, it's much more than a role, it's a fundamental role. And this is in fact the Soliton resolution conjecture that was made in many cases for many Hamiltonian problems in particular, not only Hamiltonian by the way, but in particular Hamiltonian problems, that the long time behavior of such of solutions of such an equation is that they decouple as a number of Soliton solutions plus some radiation. And this is the, let's say, general version of the Soliton resolution conjecture. So what I'm going to tell you about today is the proof of this conjecture. So theorem. So I need a little bit about the data, which is not too much. So of course I'm dealing with real valued functions here, of course. So they are always real valued. And I will assume a little bit more decay. And moreover, something that we needed to add, that there exists some constant and some L2 function such that x squared u0 of x equals constant plus v0 of x. So these are my assumptions. Notice that these assumptions are fulfilled by any linear combination of RPs, by any Schwarz function, by any, in fact, rational function with no pole on the line, which are in L2 and such x, the rational functions in L2. So you have plenty of data which satisfy these assumptions. Then I claim that there exists an n, which is the number of soliton which will emerge as t goes to infinity. There exist complex numbers in C+, as here, with different imaginary part. Of course positive, but they are different. And there exist functions in H1, real valued, such that that's exactly what I told you, u of tx, as t goes to plus or minus infinity, equals the sum from j equals 1 to n of rpj of x minus cpjt. So these are the cpjs, 1 over imaginary part of pj, plus some scattering term corresponding to a linearization at 0 of this equation. So you forget about that. E to the t dx mod d acting on u infinity plus or minus, plus some small term u of 1 in h1. That's it. So this is the theorem. Any solution of Benjamin-Ono with that kind of data behaves like this as t goes to plus or minus infinity. Look, notice one thing which is very important. As t goes to plus or minus infinity, the pj's are the same. But the guys here are not the same. Okay, so the radiation profile are different. They don't differ that much. They differ by a Fourier multiplier which is unitary, so it's not much. But what is really strange is that these guys, these pj's, are the same for plus and minus infinity.
Are they explicit or?
Yes. And this is one of my of the part of my talk, of course. I'm going to tell you how to guess these pj's and these u infinity plus or minus from the data, from the u0. And they are related to something which is wonderful, which is called a lax operator.
So that's integrability.
That's integrability.
Another question.
Yeah.
Does it imply that, in particular, these traveling wave solutions are unique and stable?
Yeah.
So you need.
Yeah. We knew that, but you knew that already. But yes, they are. Yeah. Absolutely. The uniqueness of these traveling waves was in fact proved. I forgot to mention it, so thank you, Sergio. The uniqueness was proved in 1991 in a nice ACTA paper by Amick and Toland. So Benjamin observed that these were solutions. Amick and Toland classified all the traveling wave solutions.
And the stability also?
That was done a little later on. But now we have much better, and even in H minus half plus epsilon, whatever. And we have an excellent stability of these guys. Okay?
Can you say about small o1?
Small of 1, which is a remainder term in H1.
Any rate, or it's just
Any rate, no. Not at this level of generality.
Okay.
In some cases, I can have some rates, I will tell you. But this is one of the difficulties, is to prove that this guy is going to 0. And we were happy enough to prove this already. Okay, but that's, of course, an excellent question. All right, so, of course, this is probably not the
And this is not a generic issue, right? Like, you know, there are many conjectures, say, general relativity, there is a similar conjecture, but it's supposed to be only generic.
Yes.
Generic initial.
Here it's true for all data. All data. No exception. Of course, if I try to relax that kind of thing, for instance, XU0 in L2, then I might not have a pure scattering, I might have modified scattering. And this may be even more complicated if I just assume U0 is just in H1, but no decay. In that case, it's a little bit like when you look at cubic nonlinear Schrödinger equation in 1D, defocusing. We know there is some scattering, but only modified scattering. And this is impossible to have pure scattering in that case. Here you may have pure scattering under these situations.
Okay. So, sorry, just one more question. So, is there a similar result known for KdV?
Excellent question. That was what I wanted to tell you now. Okay? So, similar results. There are, in fact, two classes of similar results. The first ones correspond to integrable PDEs. such results were made in 1983. It was only partial, but it was called the emergence of solitons in the KdV dynamics, and it was done by Eckhaus and Schur, physicists. Okay. Then it was made more precise. Well, all these things, of course, use inverse scattering transform, which I'm not going to tell you about, because this is not the tool I'm going to use. I'm going to use another version, another formulation of integrability. Of course, I will use integrability, but in a different way, which is hopefully simpler to use. But Eckhaus and Schur, and then in a little later, I think it was something like 1919 watts, sorry. Yes, it was in 1994. There is a famous paper by Deift, Venakidis, and Gerard. Okay? This is for KdV. This is for KdV. But then you had several results on the same kind of things for MKdV, by Chen and Liu, on cubic focusing NLS, by, many people around Jenkins and McLaughlin, Ken McLaughlin. There are DNLS by Jenkins, Liu, Paris-Saclay. Paris-Saclay. Well, in the 2000s. What is specific, in some sense, it's the same kind of approach here, is really this inverse scattering transform, originally using the so-called Gelfand-Levitan-Marchenko integral equation, and then revisited by Deift and Zhao through Riemann-Hilbert problems and what they call the nonlinear steepest descents, etc. This is just for people who know about that. I'm not going to use it. But this is just to answer your question. This is relatively heavy, and in fact, it's not so easy to find such a simple statement in these papers. You have usually more precise decays, but in some part of space-time, but not the whole space-time, etc. Second class of equations, non-integrable PDEs, but with, of course, specific properties, and in particular, energy critical. So, and the techniques are completely different. They are related to, different approach. You should ask about Frank about that. So there are a list of papers by Duikertz, Koenig, Merle, and also by Jendrej and Lowry. So these are typically energy critical wave equation with radially symmetric equation, or radially symmetric solution, or wave maps with some equivariance. So in that case, it's a little bit more complicated, but because the solution is not, you might not have a global solution. You might have some blow-up time. But in the case of blow-up, you can also have some kind of Soliton resolution. Mutatis mutandis, let's say, okay?
No doubt.
Yeah, exactly. So the techniques are completely different. They use, in particular, very nice property of the wave equation called energy channels, but also, of course, the modulation, Martel-Merle modulation techniques. But this is strongly related to the energy criticality. Okay? And there are also some results. It's not in the Hamiltonian case, but there are also results by Kim and Merle for the heat equation for the harmonic maps. So it's not, of course, in that case, it's not Hamiltonian, but there are also very nice properties of that kind. Okay, this is very recent. Okay, it's really the last few years. Okay, so this is the situation. So my purpose today, yes.
Can I ask about the theorem? So there's that slightly mysterious assumption about x squared U naught.
Yeah.
That must have to do just with the Benjamin-Ono. That's something.
Yes, it has to do, you know, with the structure of this guy too.
I see. So that's special to that.
Yeah,
to this
yeah.
equation. And it almost implies the x U naught in H1, right? It almost implies it.
Almost. In fact, you can relax this one. What I really need is x U0 is in L2. This is really fundamental, I will tell you.
It is implied.
Yeah, of course. Okay, but so we were hoping that we could kill this guy, but maybe we'll be able, but for the moment we are not able to do so. I will tell you exactly why we need it. Okay, so maybe other questions? So what I'm going to do this afternoon is to tell you how to characterize the P1, Pn and these profiles, scattering profiles, in terms of an operator which is associated to the initial datum U0. And this is related to the integrable properties of this equation. And then, of course, I will tell you how to prove this. So again, it's a different approach from these ones. Well, it's probably closer to the first one, but again, I think it's simpler. Okay.
It probably applies in those other cases. Also.
Yeah,
the method probably applies in all cases.
Yeah. By the way, thinking of this, in the case of KdV, for instance, the PJs, which are proved to emerge also in this equation, they are different as t goes to plus infinity and minus infinity. So we have a strong difference between Benjamin-Ono and all these integrable equations. It's interesting. For the moment, I don't have, I mean, I can tell you why, technically, but I don't have a philosophical explanation of that. Okay. So let's go to the integrable properties. So let me talk about integrability. Hopefully on this board only. So integrability in that case means what? I need an auxiliary Hilbert space first. In the case of the KdV equation, the Hilbert space is L2 on the line. So people think that's, okay, that should always be the same. This is not the case here. And this is related to the fact that the operator mod D is non-local. In fact, to tell you the whole truth, people were a little bit frightened by this non-locality, and all these techniques could not really be applied because these techniques were really based on differential operators. And here we don't have local operators. So we have to deal with something else. And my message this afternoon is that this difference, which makes so many people afraid, is in fact a chance. And in fact, it makes the analysis simpler. We will see why. Okay, so what is my Hilbert space? It's called the Hardy space. These are functions on L2 such that the support of the Fourier transform is in 0 infinity. Now there is a very nice theorem in functional analysis which tells you that this function can be extended as holomorphic function in the upper half plane. Subject to that kind of properties. So you take the L2 norm square on all horizontal line and they are bounded, okay? So this is the so-called Cayley-Wiener theorem. So this is my Hilbert space. On this Hilbert space, I need to define nice operators. So these operators I need are called Toeplitz operator, given an L infinity function on the line. I define the Toeplitz operator on H to be the operator which sends f to pi of bf So what is pi? Pi is the Zeger projector, sometimes called also the Cauchy projector, sometimes called also the Riesz projector, which is the orthogonal projector from L2 to H. Okay? Sorry. So if you prefer, pi is given by the following Cauchy formula. So pi f is an element of H, so you can think of it as a holomorphic function, while f is just in L2, and pi f is just given by this, which explains why people call it the Cauchy projector, of course. This is the integral formula of Cauchy. All right, so this operator is bounded. It's very easy. And it's also easy to see that its adjoint corresponds to the same operator when B is replaced by its conjugate. It was that kind of operators which were introduced by Otto Toeplitz in 1913 or 15, I don't remember. Okay, now I'm going to apply to any solution of my Benjamin-Ono equation a family of unbounded self-adjoint operators of this auxiliary Hilbert space. So given a function u, let's say in H1, but it could be in L2 in fact, I'm going to define Lu, which is 1 over I ddx minus Tu. So this is unbounded and self-adjoint on H. Notice that since I'm on H, since the Fourier transform of f is supported in the half-line, positive half-line, the operator here is positive. Because in Fourier transform, you see xi, f hat of xi square, and xi is positive. Okay, so it's a positive operator. This one is, well, almost bounded. If u is in H1, for instance, it would be. Otherwise, it's relatively bounded. So this operator is bounded from below. Okay, so it's a nice unbounded operator, self-adjoint, unbounded, but bounded from below. Now, I claim it's a theorem which is known for quite a while, about the 80s. Several people observed that, Nakamura, a little bit before the 80s, maybe Ablovitz, Focas, Karp, Newell, well, whatever. Many people realized that maybe in slightly different formulation, but that U is a solution to the Benjamin-Ono equation, BO, which is up there. If and only if. So I look at this operator Lu, depending at every time t. And I write this, which is called a Lax-pair identity, where Pu is an anti-self-adjoint operator of that kind, T mod du minus Tu square plus Lu square. This Lu square could be erased because it commutes with Lu. But people usually like to add it. And so this is the notation that was used by Kilip and Vishen. L is for Lax and P is for Peter, of course. So this is a Lax pair. And that's typically what Peter Lax introduced in 1968 for explaining the observations about KdV, which were made by Gardner, Green, Kruskal, and Muir. Moreover, so for KdV you have that kind of structure. But here you have something better. Moreover, I can also look at my solution U and make it an element of H just by projecting U. So if I project U on the RD space, I get an element of the RD space, and I can try to look to a PDE for that. Well, I claim that this PDE is just this one. So this is typically completely impossible for KdV. So it's some kind of better property, further property of the Lax pair for Benjamin-Ono. So this operator Pu comes here, but also comes in the reformulation of my equation. You could say, well, this equation seems more complicated than the one I see here. Let me give you immediately an application of that concerning conservation laws. Application. Conservation laws. So I pick any Borel function on the line, and I look at the following quantity, EH of u, which is H of LU in a product acting on pi u, pi u. So pi u is an element of my Hilbert space. Let's say that H of LU, well, for simplicity, for the moment, assume that H is bounded, so that this is a bounded operator. But H, in fact, could be growing like a polynomial. If you know a little bit more about Pu, then I claim that this is a conservation law for every H. In other words, the spectral measure of the operator LU associated to the distinguished vector pi u is a conservation law. This is very nice. And how would you prove that? It's extremely simple. You just have to look at this equation and this one. Take the derivative of this. When you take the derivative of this, you take the derivative of this function of LU, which satisfies exactly the same bracket identity with the same Pu. And then you take the derivative of pi u here and the derivative of pi u here. Now remember, if you unfold the bracket, you will have two terms, plus 1, plus 1. And remember that Pu star equals minus Pu. It's extremely simple to get that ddt of EH of u of t is 0. But now, if you look at what are these guys, for instance, for h of lambda equals lambda to the k, and k between 0 and n, you get that all these guys, all these hk of u control the hk over 2 norm. And this is true for any k, hn over 2, sorry. So if you look at all these conservation laws, starting with the L2 norm, of course, for h equals 1, you get many, many conservation laws which allow you to control all the hn over 2. And you could, of course, take fractional power, whatever. You get this bound on hs norms that I was announcing. So you see, just this property tells you that you always have bounds on all the small spaces. Okay? So now, I need to tell you a little bit more about the spectral theory of such Lax operator.
So all these conservation laws are coercive now, or?
Together. If you look, for instance, at, well, of course, L1 it is. But then you take the first two, you will get h a half. The first three, you will get h1, etc., etc. So yes, they are. That's wonderful. From 1/2 to 1/2. Okay? So what's the spectral theory of LU? So let me look at LU0, because this is what I'm going to tell you. And this is where I will be able to tell you how to identify the parameters P1, Pn, and U infinity plus or minus from this spectral theory. So what is the spectral theory of LU0? It's very simple. You can prove that the spectrum of LU0 is absolutely continuous from 0 to infinity. And on the negative part, it's made only on a finite number of eigenvalues. And moreover, these eigenvalues are simple So this is of course a consequence of the part of the assumptions I made in the theorem. I don't need all the assumptions, but at least part of them. Okay, u0 in L infinity, and xu0 in L2, and that's enough.
And the n is the same n?
Yes, that's what I'm going to tell you. Now I claim that the CPJs, well, the PJs are related to the pure point spectrum, the lambda J's, while the U infinities are related to the absolutely continuous spectrum. So for these lambda J's, of course, you can define eigenfunctions. Let me make them normalized. And I claim that Pj is just minus, well, 1 over 2 I pi, let's say, inner product of dx phi j hat. So this is a Fourier transform, standard Fourier transform in L2. And this is my Pj. In particular, the CPJ, if you integrate by part and use a little bit of these properties. So these properties were made, I should have mentioned it, were established by Yilun Wu in 2016. He's now in Oklahoma. CPJ is 1 over 1 Pj, and this is also twice the absolute value of lambda j.
What is UJ?
Sorry?
It's
It's U0. Sorry. It's a 0. Sorry. So I give you this LU0 operator, make spectral theory, look at the eigenfunctions, and this gives you immediately, this formula gives you immediately the PJs. So how do you get the U infinity now? Well, you have to introduce what are called generalized eigenfunctions or Yort functions. So for every lambda positive, there exists a unique function m plus or minus, it depends, m plus or minus of dot lambda, which is in L infinity of R, and which is a solution of L u0 m plus or minus equals lambda m plus or minus. So it's a generalized eigenfunction, and you fix it by impose it at e to the minus I lambda x, m plus or minus of x lambda, tends to 1 as x tends to plus or minus infinity. So what could prove, it's not completely trivial, that's what we did with Louise and Peter, and also another a postdoc of Peter called Elliot Blackstone. We proved that such things exist, are unique, and then I can define the distorted Fourier transform associated. And the distorted Fourier transform for this, there are two, in fact, for plus and minus. So given a function f in L2 plus, I can define a function f tilde plus or minus of lambda in L2 of 0 infinity by the formula, well, the thing that you would do if u0 was 0, m plus or minus would be, of course, e to the I lambda x. And in that case, you would take, of course, this integral. Okay, so you can prove that exactly as for Plancherel theorem, that this integral for f in L2 plus is in fact well defined as an L2 function on 0 infinity. And you have a distorted Plancherel formula, which in some sense makes the balance of the whole L2 norm of f, which tells you that for every f, you have the sum of ed dot tj's square. These are the parts corresponding to the simple eigenvalues, plus 1 over 2 pi, integral from 0 to infinity of L tilde plus or minus lambda square d lambda. And now I claim that u infinity plus or minus, the one which are in our theorem, They are characterized by their Fourier transform for every lambda positive, and their Fourier transform are exactly the distorted Fourier transform of pi u0 corresponding. And this is the theorem. So the theorem, it tells you that I give you a u0, I look at this spectral theory, these eigenfunctions, I define pj's with this, I define u infinity like this, which are the distorted Fourier transform of pi u0, and then we have the theorem.
Does it mean that if you linearize around any further value of u, you get always the same discrete spectrum? If you look at the evolution of u from the dot,
the evolution of u is always the same. You have exactly the same spectrum, of course. Oh, sorry. Yes, this you can see it immediately here. It's an old result by old observation by Peter Lax. As soon as you have such a thing, you can prove that LU of t and LU0 are unitarily equivalent by a unitary operator, which is defined like this: U capital U dot equals PU capital U, and capital U of 0 equals identity. So that's, of course, you have exactly the same spectrum for all time. While these guys are changing a little bit, but not too much, like a factor, a unimodular factor like e to the it lambda square, typically. So this is nice because you have some corollary. Okay. About special cases. I told you about this general theorem, but now it's interesting to see some special cases. Is it possible, for instance, that n equals 0? So the purely radiative dynamics. Yes. It's equivalent to the fact that there are no eigenvalues. But no eigenvalues means that the operator is positive. Now, if you look at the structure of this operator, LU, which is here, and you look at LUF, this is exactly DFF, which is a positive term, minus integral of U0 F squared. So, for instance, if U0 is non-positive, this is always non-negative. So a consequence is that if I give you an initial datum which is non-positive, then the dynamics are purely radiative. No solitons. On the other hand, you can say, is it possible that you don't have radiation? This is equivalent to the fact that you don't have radiation at t tend to minus infinity or plus infinity. And this is equivalent to the fact that U0 is a multi-soliton. So what is a multi-soliton? It's a sum of solitons. RPJ tilde. The PJ tilde, they are different from the PJs, by the way. They can be the same, for instance, while the PJs are different because their imaginary part are different. So, so the picture, you know, the picture, I forgot to give you the picture of this theorem. If you look at the graph of your function u, so you will have some solitons like this. But the situation is the opposite of a group photo as we had this morning. Namely that the big are ahead and the small are behind. Because the small have a soup norm which is precisely equal to their velocity. So if you wait for time enough, the big ones are ahead. So it's very bad for a group photo. Okay? But and then you have this wave equation. Okay? So this is the thing. So I have maybe a couple of minutes to tell you how to prove that. Well, of course, I've cheated. I've cheated because this integrability in that case can be formulated in a very, very efficient way. I have a representation formula. A little bit like the representation formula given by Sanjin in the beginning of his talk. Except that the Fourier transform must be, well, it must be changed and replaced by some kind of distorted Fourier transform. But I don't even need distorted Fourier transform. So I need to, introduce finally a last operator which is so important on H, which is the operator X star. So what is X star? X star is the adjoint of the multiplication by X. Multiplication by X, if you look at L2 of R, of course it's an unbounded self-adjoint operator. If you work on H, it's no more self-adjoint. It's symmetric, of course, but its adjoint is bigger. And the domain of X star is just those functions in L2 plus such that the Fourier transform on 0 infinity is in the Sobolev space H1, and then X star is just given by the Fourier formula that you could write for the Fourier transform of XF, except that in our case it's only for Xi positive, and this function, of course, it's supported at Xi for Xi positive, and for Xi negative it's 0. So here there is a limit, and this limit may be not 0. May not be 0. So this limit, I call it I plus of f. This is just the limit of f hat as Xi tends to 0 plus. And now I can write, well, let me write it down here because I don't have that much time more left. I can write the representation formula for the solution. So for every u0 in H1, I don't even need any kind of decay. It's very general. You can have even a formulation for L2. Real valued, of course. The solution U of my Cauchy problem is given through pi U. So for every Z in C+, pi U of Tz is given by this formula. 1 over 2i pi I plus of X star minus 2t LU0 minus the identity minus 1 acting on pi U0. That's it. So this is the tool which replaces inverse scattering. It's just a formula. You start from your datum, you look at its projection on the Hardy space, and you look at this resolvent for every Z in the upper half plane. This resolvent you can prove it's well defined. You can prove, of course, it's also in the domain of X star, and so you can take its I plus, and again it's 1 over 2 I pi, some kind of deformed Cauchy formula, and you get the solution. That's it. So now, how to prove? Well, it's even with this you have to work, okay? In fact, what we can do, I have probably something like 5 minutes. Is that correct? So maybe I can explain this a little bit. So the strategy of proof is the following. You make a reduction to weak convergence. So Sergio doesn't like weak convergence, but here this weak convergence would be very nice it will be transformed into strong convergence.
Well, that's what I like.
So, but okay, so there are two kind of weak convergence I need. Well, if you look at this decomposition there, you can guess what kind of weak convergence I'm going to do. So this is first the Soliton fishing, what I call Soliton fishing. For every j, I look at u of t and x plus cjt, cpjt, and I want this to go weakly to rpj of x. Well, that's what you expect, okay?
So that's a way to identify.
Yes,
correct profile.
exactly. Right. And now you identify also the radiation capture, and you do that. As t goes to plus or minus infinity, u infinity plus or minus. Now, the nice thing is that we don't have u, but we have pi u. Well, of course, you can replace this weak convergence in L2 by a weak convergence in H on pi u. But the nice thing about the Hardy space is that this weak convergence in the Hardy space is equivalent to a pointwise convergence in the upper half planes. So your z here is fixed. And it helps a lot. Because then you can use the spectral properties of your LU0 to get the weak convergence. Now, why is weak convergence can be transformed into strong convergence, and I will stop by this. Well, you just do what we learn to our student. You look at this term, which is the difference between you and all these guys. The one I would like to make going to 0 in H1. So let's prove it going to 0 first in L2, because then it's not so difficult to go to H1, u infinity plus 1, sorry. So you look at this guy, and you take the L2 normal square of that, and you expand. If you expand, you will get the L2 normal square here, but this is u0 square because of our conservation law. Then you will get the inner product of these guys, but they are exactly given by this thing, and they come twice. You will also have the inner product of this guy with this. They come twice, and this gives you that. Then you have the squares of all these guys. It gives you the same quantities, but just once. And finally, you have all the rectangle terms, which are in fact 0, because the CPJs are different, and because this guy is dispersive. So you use dispersive inequality for Schrödinger. And you get that this is in fact sum of RPJs square minus u infinity of plus or minus square. And then this guy, you compare to your distorted Plancherel formula active, and you apply it to pi u0, and you get that this is always 0. So it goes to 0. So using this weak convergence, you get strong convergence by means of this spectral theory in distorted Fourier.
You don't have to do an induction on n.
No, not at all. Not at all. It's true for all n. I know that n is finite due to this nice paper by Yilun Wu. There are examples where n is infinite. If you don't have enough decay, that's for another story. Okay. I think I'm done. Thank you very much for your attention. And happy birthday.
Any questions?
Well, so the same kind of question. So this is a new method. It's very, very nice. I think it's connected to this work of Killick and
a little bit, yes, at least in this interpretation. But in fact, this explicit formula, I proved it before. It was a paper in 2023, which I was not expecting. So it's an old story to explain. It was due to a lecture course I had to do in Tunisia, where people told me, you should tell us about integrable equations, but we have a requirement, absolute requirement. You should discuss at least 2 different equations, not one. So I discussed an equation that I was working on for quite a while, which was called the Zeger equation, and the Benjamin-Ono equation, on which I was working originally with my good friend Thomas Kepler. But we were on the circle. And I realized that at some point, I knew something about the Zeger equation, which I didn't know about Benjamin-Ono, and I wanted to know why, which was, in fact, this representation formula. And I realized there was such a representation. So this Zeger equation helped me to find this one.
Yeah. So what is the analogous of, let's say, KdV or for all the other integrals?
I don't know any analogous for KdV.
But in principle, could you add something similar?
I'm not sure. I'm afraid I'm not sure.
So it's because of this that this method might not apply to prove the results.
That's what I wanted to tell you in the beginning when I told you this non-local thing is a chance because we have all this RD space structure, which is in fact, which helps us. It helps us. So for the moment, I'm not unable to recover all these results, all these nice results by my method, because I don't have this method for these equations, surprisingly.
Do you know if this behavior of like large waves in front of the small one is observed in nature in the regime where BO is observed?
For KdV, it's also observed, I think.
Okay, and for BO, do you know?
For BO, I don't know, but at least there are numerical simulations that were made by Yvonne Alama-Bronsard last year, which completely confirmed that. I mean, it's very, very neat, because she found a simulation which is in fact using a version of this representation formula, which is extremely accurate for long times. The problem of these equations is that because they are evolution equations, numerically the long time estimates are very bad. You have exponential times. But here she doesn't have exponential errors, and so she can see behaviors for very long times, and she sees this. Yeah.
Wait, is it not explicit from the formula? So from the formula, if the CP, the larger CP.
Yes, it's explicit. But yes, the gentleman asked me about confirmation by nature. I don't give a confirmation by nature, but at least a confirmation by simulation, okay, which is in some sense in between, I would say. Sorry.
Okay, a question is how much it allows the perturbation? For example, the intermediate non-wave equation.
That's an excellent question. For the moment, because there is this equation which is called intermediate long wave, which corresponds to the same problem studied by Alex. It's a long wave, but for finite depth. In that case, the mod D operator is replaced by another Fourier multiplier, which is cotangent delta D, where delta is the depth. Okay. For this, there is still a lax pair, but at this stage, nobody knows how to use it for long time behaviors. And in particular, for the moment, I don't know how to extend this equation, this formula, to ILW. But you are right. We would like to know what's going on when delta, the depth, is going to infinity, and to look at perturbative analysis on BO. This is in fact a project I have, but for the moment we don't see.
So just a philosophical question. So in what sense is Benjamin-Ono better, let's say, as a model problem than the other ones?
It's a very good question. In fact, I'm convinced it is for the reason that we have much more structure, and in particular this structure, this reformulation structure, and this very simple formula for conservation laws. If you look at KdV or NLS,
it's more complicated.
Much more complicated. So it's a mathematical answer. I agree.
But nature likes.
Nature likes it's not so clear because KdV is shallow waters. Here it's infinite depth. Well, I don't know.
I'm just trying to help.
Yeah, thank you.
So the stronger assumption, the x squared decay, how does it fit into this?
Yes. Okay, so this stronger assumptions comes in this part. So if you replace this at the level of pi u, you have to study some oscillatory integrals. And these oscillatory integrals involve the profiles of these functions m plus or minus. These profiles, you have to take derivatives of them, both on the physical space variable and on the spectral variable. And for this, you need a little more decay of that kind. For the moment, we cannot avoid that. So that's exactly where we need it. It's only at one point. And this is in the scattering part. In the Soliton fishing part, you don't need all these things. I mean, you just need this part, and then it works very well. So the main part of the paper, in fact, is here.